Welcome back. In this video, I'm going to provide you with some opportunities for some extra practice problems dealing with solubility, and then I'll walk you through the solutions. You should pause the video, read through the question, and try and solve this on your own, and then I'll talk you through it. Welcome back. So we want to know which of these substances would we expect to be the least soluble with water. How do we evaluate this? We know that solubility is based upon molecules having similar intermolecular forces. We use the phrase like dissolves like. So if two molecules have similar intermolecular forces, then they'll be very soluble. They'll dissolve well together. We know that water is a small molecule, it's very highly polar, and can participate in hydrogen bonding. When you evaluate each of these 5 molecules, we see that they also have polar regions and can interact through hydrogen bonding. So the one that's going to be least soluble is the one that's least like water in terms of its overall characteristics. When we looked at organic molecules before, we saw that molecules can be both have polar regions and nonpolar regions. And so molecules that have a more nonpolar surface area are going to be less soluble in water. When you evaluate each of them, molecule A looks like is maybe about 50-50% carbon versus the polar regions. Molecule B, however, has a very large nonpolar region, that the ring structure, and that's larger than the proportion of polar to nonpolar region to polar region for any of the other molecules. So we might say here that this is somewhere around 50% nonpolar, where this is much, much higher. This is maybe 80-85% nonpolar. It has a very large nonpolar ring. This might be 75% nonpolar. This is much, much smaller, closer to 50, closer to 50. Now, the exact values here, I'm kind of just making up numbers here that look reasonable based on the structures. You should be able to tell that this region here is definitely larger than any of the other nonpolar regions. Therefore, B is going to be the least soluble in water. Here's another question. Pause the video and try this one on your own. Welcome back. So we're told that you have a bottle of seltzer water at 25 degrees Celsius, contains carbon dioxide with a partial pressure of 2.36 atmospheres. You're given the Henry's law constant and want to know what's the mass percent of carbon dioxide in the water, assuming that it only contains water and carbon dioxide, and the density of the solution is 1 gram per milliliter. How do we solve this? Well, we can tell that we're going to use Henry's law, given its constant and the fact that we're dealing with a gas being dissolved in water. And we know that Henry's law allows us to calculate the molarity of dissolved gases in water. And we've already related molarity to mass percentage in previous videos. So let's go with that route. We can solve for the solubility or concentration of carbon dioxide in water by multiplying Henry's law constant times the partial pressure of the carbon dioxide. Now, we want to find the mass percent. That's equal to the mass fraction times 100%. Mass fraction is defined as the mass of the solute over the total mass. Since we're given the molarity, or we solve for the molarity, we know that that's equal to a ratio, the number of moles of carbon dioxide per 1 liter of solution. When you write it out this way, it's easy to see that all we need to do is convert the moles of carbon dioxide to mass and the volume of the solution to the mass of the solution. We can find the mass of the solution by taking the volume, converting it into similar units, and multiplying by the density. That gets us then our mass of solution of 1,000 grams. The moles of carbon dioxide can be multiplied by the molar mass to find the grams of carbon dioxide. Mass fraction is taking the ratio of those two and solving. To find the mass percent, we multiply the mass fraction times 100%. That's it. Let's do one more question. Pause the video and try this one on your own. All right, for this question, we want you to estimate the molarity of a saturated solution of potassium nitrate at 50 degrees centigrade, and you're given the density. How are we going to do that? Well, we know that molarity is the moles of a substance per volume of the solution in liters. From the graph, we can tell that we have a total mass of water of 100 grams. And from the graph itself, we can determine the solubility. So at 50 degrees, we see that we have, within 100 grams of water, we have 90 grams of potassium nitrate. Now we can take that information by defining molarity as moles of potassium nitrate per liter of solution, and using the known information, we can now solve. So we know that the mass of our solute is 90 grams. The mass of the solution is 190 grams. We need to find now the volume of the solution in liters. We can use that now that we have the mass of the solution, and we need to find the moles of potassium nitrate, knowing it's the mass that we have. So we can find moles by taking the mass and dividing by the molar mass. That means we have about 0.9 moles of potassium nitrate. The volume of the solution in liters is found by taking the mass, dividing by the density. That will get us a volume of 136 milliliters, or 0.136 liters. The molarity then is found by taking the moles and dividing by the volume of the solution in liters. 0.89 moles per 0.136 liters gets us 6.5 molarity. That's it for this video. Thanks for watching. Have a great day.